in the participant list. So my name is Angus McNabola. I am going to be the chair of this morning's session. For those of you who haven't met or weren't here the last time, I'm a professor in energy and the environment at the School of Engineering in Trinity. And today's webinar is on recovering heat from drain water, looking into a little bit about the opportunity to do this and to save energy. So, sorry, one moment. So just a little bit about the program. So as some of you have already seen, we're running a sustainability webinar series on a variety of topics. The last time we were looking at exploring micro hydropower. Today we're starting off one of two sessions on recovering heat from drain water or from wastewater. We also hosted a panel discussion earlier on this idea, particularly for leisure centres, which was a very interesting talk. So today is on wastewater heat recovery, a little bit on the background, the feasibility of doing this, and the opportunities for implementing the recovery of heat from wastewater in the Ireland-Wales region, and that being as we are funded by the Interreg Ireland-Wales programme. But of course, the application of this is valid for anywhere with a similar sort of climate to Ireland and Wales. In about 2 weeks' time, on the 24th of March, we will have another session on the recovery of heat from drain water. It's called Making It Happen. In that case, we'll be going into a lot more detail on a pilot installation that we did in the UK at a commercial kitchen. So it goes into the detail of the design and performance of that. So our speakers today will be mentioning that, give you a little overview of it, but we won't have time to go into the nitty-gritty of it. So there'll be more details on that later if you are interested. And then our last webinar in the current series is on benchmarking of water and energy. And so that one will be coming up later in April. So before we start, just a little bit about what the Dúr Uisce project is, for those that haven't heard before. So this is a project that started in 2016 as a collaboration between Trinity College Dublin in Ireland and Bangor University in Wales, around looking into technology and also policy on trying to make the use and supply of water more energy efficient. So we have been and continue to look into the development of a number of technologies. Obviously, one of them is the recovery of heat from wastewater. So we are going into the development of heat exchangers for that specifically, but also looking into it from a policy point of view. If you were at our webinar series about a fortnight ago, you will have seen we were working on the recovery of hydraulic power from water networks, micro hydropower. We're also doing things on control of water networks, on eco-design, on environmental impact, various policy measures. And importantly, we're trying to tell people about it in a sort of a network of interested parties, as we're doing today. And we're very grateful to our funders, obviously, who support us very generously. This is the Ireland-Wales programme. As you can see in the image there, the Ireland-Wales programme area is the east of Ireland and west of Wales, approximately. So on to today's session is going to be around an hour in total, and we're going to, when I hand over to our speakers, we'll have about 45 minutes or so of a presentation, which we hope will be followed then by any questions you might have. So in terms of the session etiquette, I guess we're probably all quite used to this at this stage. Please have your camera and microphone off, and if you've got questions, please put them in the chat as they occur to you. We'd also be very grateful if you could introduce yourself in the chat, or at least maybe change your name to your actual name. Sometimes when you use Zoom, it appears as your username, and so it's not actually clear as to who you are, and to help us try and make this a bit more interactive and like an actual meeting, we'd like to say, like to know who you are and what you're interested in or your background. So please do introduce yourself on the chat. I should also mention that this session is being recorded. I'm sure your Zoom is already indicating that, so there will be a recording of this later, which you can get via the website, our Duarishka website, and the link to which will pop up later on. Okay, so on to just introducing our speakers. We have two speakers today, both research associates in Trinity College, Dublin, and both working primarily on the recovery of heat from wastewater. So this is Dr. Ajit Pratap Singh and Dr. Madhu Murali. We're going to start off the session with Ajit, who's going to introduce the background to drain water heat recovery, and then hand over to Madhu, who will deal with a little bit about the feasibility of doing this and some of the opportunities for implementation. Ajit has a background in mechanical engineering and has worked previously on other sort of heat transfer applications in solar energy for domestic heating. And Madhu is from a wastewater treatment and collection background, and has also worked in the water sector for several years. So hopefully both of their experience in the recovery of heat will be of interest to you. So without further ado, I'm going to hand over to Ajit to kick off the webinar, and I'll stop sharing. So Ajit, if you want to go from here.
Yeah, thank you, Angus. I'm going to share my screen. Good morning, everyone. In today's sustainability webinar, we are discussing about the heat recovery from the hot wastewater, which is coming from the various locations. So in this, we are discussing about an overview, background, the technical and the economic feasibility, and the opportunities and the benefits for after the implementation in the Ireland and Wales region. So I'm Ajit Pratap Singh, is a researcher in a Durisha project. We'll proceed with, and then I hand the back to the Madhu to discuss about the technical and the economic feasibility of the heat recovery from the wastewater. So this is the presentation outline which we have prepared for this webinar, starting from an overview, starting from the background, and then followed with the case studies, and then improving uptake. We started with the background, that this is a schematic of the flow diagram of the cold water which is coming from the supply and then goes to the heating unit, that is a primary heating unit, in which there is a continuous heat input via conventional fuels like oil, wood pellets, and many other conventional resources. So after taking the heat, the cold water get heated up and goes to the various applications. And then it goes to the drainage system, that is sewer network, and then goes to the wastewater treatment plant. The last three steps, the applications, sewer drains, and wastewater treatment plant, associated with a high heat loss. And it has the high amount of energy potential to recover it. But as of now, we are just wasting, and just effluent is directly going to the sewer drains. So this slide is showing about the few applications that is a major known applications in everyday life. So they started from the kitchen sink, shower, washing machine, and especially the hospitality industry. So EAs of comfort in the hospitality industry is at the top. So hot water requirement in the colder countries is a major requirement. So the hot water at the various applications at the outlet, that is going into the sewer drains and then wastewater treatment plant. We are recovering this heat which is going earlier waste as a waste into the drains. We are recovering the heat from the hot wastewater and giving this additional recovered heat directly as an input to the primary heating unit, so that the primary heating load of the heating unit will get reduced, and we could be able to save the monthly electricity bills, and there are several environmental benefits by reducing the carbon emissions. So if we're talking about the benefits of the heat recovery, that if we talk about the estimation that 40% of the energy which is used for heating up the cold water in the European Union is used to generate the energy via conventional fuels like oils and many other resources. And the quantity of the recoverable heat in UK hospitality sector alone is around 1.24 terawatt hour per year. That is equivalent to the burning of the 150,000 tons of coal per year. So there's a huge carbon emissions. It has the adverse climatic effects, and which can be seen in various severe diseases related to the respiratory and many other diseases. And these sources of heat are mostly non-renewable, based on non-renewable resources. Means the energy comes from coal, oil, and wood pellets, and many other conventional resources that are the huge emitter of the carbon emissions in the Ireland, Wales, UK, and most of the countries in the European Union. So this is a statistics that is telling about the amount of the heat which is generated via renewable energy resources. So we can see the Sweden is at the top, 66.1, and Ireland and the United Kingdom is at the bottom. So for Ireland it is 6.3, and for United Kingdom it is 7.8. So there's a huge potential hidden which can be recovered from the hot wastewater which is coming from the various locations, and can be recovered for the economical as well as for the environmental benefits. So the wastewater in the recent European Union Green Deal policy, that the wastewater which is coming into the drainage system is recognized as a renewable energy source. So this is a major advantage, that we can take this advantage, the huge energy potential which is embedded in the hot wastewater, which is going waste into the sewer drains, we can recover to justify the economic as well as the environmental benefits. So we are naming this term as an heat cycling, because we are recovering the heat which is earlier going as a waste into the drains. So let's start heat cycling. These are the major components, and or we can say the heat exchanging devices, which are prevalently used in various domestic as well as in the industrial applications. That on the left side there is a heat exchanging unit, that is a tube and shell type. In the tube, this is an example via animation. I am just trying to show that shell and tube type heat exchanger working, that the cold water from the product inlet. I'll use my laser pointer here. At the product inlet, there is a cold water supply, and that is a clean water which is flowing into the tubes. And from the shell side, there is a hot wastewater which is coming into the shell. It is at higher temperature. So there is a surface to surface heat transfer takes place here, and the cold water which is coming into the tubes will get preheated. At the product outlet, this hot water goes to the various applications and to the primary heating unit, and it will result in reduction in the monthly electricity bills. And on the right side, there is a heat pump. There is essential components, that is compressor, condenser, expansion valve, and evaporator, that is a well known. And the hot wastewater which is flowing into the sewage system is just flowing through the evaporator and absorbs and the working fluid in the evaporator absorbs the heat, and then directly giving as the recovered heat, which is recovered from the hot wastewater, directly given to the primary heating unit to reduce its primary heating load requirements. So these are the two very well-known devices. Heat exchanger is less costly as compared to the heat pump, because the heat pump consists of various movable parts and it is really expensive. So we can justify the usage of heat exchanger as well as heat pump based on its volume of the hot wastewater availability. So I will explain you in the later slides. This is a classification we made starting from the component level up to the wastewater treatment level. It is organized according to the availability of the volume of the hot wastewater availability in the sewer drains. And as we are moving towards the higher volume flow rate, the temperature quality will get decreased. So at the component level, just take an example of domestic type means housing sector, that for the one house there is a shower, and there's a heat exchanging unit placed at the bottom of the shower to recover the heat which is coming down from the drainage system of the shower, and then this recovered heat giving as the input to the auxiliary heating unit to reduce its heating load. Once we are talking about the building level, there are the various applications involved, starting from the shower, kitchen, washing machine, and various other applications. So the heat exchanging unit set up at the outside of the building, and then the heat recovered goes to the primary heating unit. For the sewer level, there is a high volume of the flow rate of the wastewater is available, but the temperature deteriorates continuously as the with increase in the volume of the hot wastewater. So the heat exchanging unit directly placed in the sewer system, and the high amount of the heat which is recovered is directly goes to the some hub unit, which is a heat which the heat is derived and giving as an input to the boiler unit, main boiler unit. So if we're talking about the wastewater treatment plant, this is at the hub that the wastewater, high volume of the wastewater, which is coming from the different locations, from the residential sectors as well as from the commercial as well as from the industrial sectors. It is directly come at a hub tank, which is having the high volume content, but the temperature is low as compared to the component building as well as from the sewer level. But the high volume flow rate is the advantage, and we can recover the heat. Maximum amount of the heat can be recovered and can be used for the district heating. This is an example of a shower system, basically in our domestic purposes or as well as in the hospitality sector, that there is a vertical type of heat exchanger is placed in the drainage system, and the cold water supply, which is at the lower temperature, the clean water which is coming from the bottom, is at almost 10 degrees Celsius, and the hot wastewater which is coming from the bathing tub is at higher temperature. So it will recapture the heat from the hot wastewater and directly goes to the auxiliary heating unit to reduce its heating load requirements. So via mixing valve, we can save our monthly electricity bills. So this vertical heat exchanger is generally made up of copper material, and the main advantage of using the copper material as a heat exchanging material is that thermal conductivity of the copper is very much high as compared to other metals. But the production of the copper is not environmental friendly in the industries. So we are also looking for some polymer based heat exchangers having the higher thermal conductivity to replace this copper material. This is an example and the schematic of the building scale heat recovery system. At the building level, there is a hot wastewater availability in the drainage system, and this wastewater is get collected in the collection tank. That is a gray water holding tank that is known as the tank which is holding the wastewater coming from the building level, and then it is incorporated with the heat pump. At the evaporator side, there is a refrigerant, and it will absorb the heat from the hot wastewater and then goes to the condenser unit. And condenser unit is known as the heat releasing unit. So the cold fresh water coming from the supply is split into two parts. That one stream is going to the auxiliary heating unit, one stream is going to the condenser side to recapture the heat from the recoverable heat from the hot wastewater. So this cold water recapture the heat and then going to the mixing bowl. And then the the cold water, clean temperature, which is at the higher temperature, is also going to the mixing bowl. And via operating this, the desired temperature could be achieved. And then it is going to the various applications and locations for its usage. This is a practical example of a drainage system made up of metallic plate that is in Zurich, Switzerland. And the cross section of this metallic plate is semicircular, and cold water pipelines is underneath this metallic plate and embedded to this one. And the hot water, you can see here, it is surrounded by the hot water, so that the fresh cold water, which is coming into the supply lines, will recover the heat from the hot wastewater present here in the drainage system, so that there is a preheating could be achieved, and there is a preheated water we can use in the laser centers like swimming pools and various other locations to reduce our electricity bills. This is an example of district heating from a wastewater treatment plant. The one of the main advantage of the wastewater treatment plant that the volume of hot wastewater availability is very much high in the wastewater treatment plant. But the disadvantage is that the temperature of the hot wastewater is not that much high as compared to the component and the building level. So we are taking the advantage from the high volume flow rate of the hot wastewater, and via pump we are circulating the effluent, and then it is directly goes to the heat pump unit, and the recapture of the heat from the wastewater taking place in this heat pump, and then giving as a direct energy input to the auxiliary heating unit to reduce its heating load requirements. And this bulk heat is directly going for the district heating for the various industrial, commercial hubs, as well as in the residential sectors. So this is a major advantage that we can recover the heat and can use for the district heating when the high volume of the wastewater is available. This is a practical example that Thames Water is a leading player in the energy transition, and they are recovering the waste heat which is embedded in the wastewater. And by utilizing this waste heat, we can save around 105,000 tons of carbon emissions. We can save over 30 years. So obviously there are major environmental benefits as well as economical benefits. So for the technical and the economical benefits, I will hand back to my colleague Madhu to explain the technical and the economic feasibility and the environmental benefits following the case studies which is performed by the researchers in the Duresha project. So I welcome Madhu to take this presentation further.
Hello, everyone. I'll just share my screen now. And all right. So we'll start from here. I hope someone will let me know if they can't see anything. So my name is Madhu. Thanks for the introduction, Ajit, and for the presentation beforehand. I'll be talking to us about some of the case studies we've been looking at and also some of our potential strategies for improving the uptake of wastewater heat recovery. So I'll start with the case studies. And yeah. So our first case study that we've looked at is Penrhyn Castle, which is a popular tourist site in North Wales. There are kitchen and tea rooms on site, which was sort of the focus of our monitoring to determine the feasibility of heat recovery there. They use wood pellets for their fuel and also use solar electricity for some of their electricity. And sorry about that. It's being a bit slow for me today. All right. Okay. So just a quick background on what the layout of the castle is like. So this is the castle itself, and these are the couple of discharge lines that go out for the drains. I think number 1 is closer to the kitchens, and 2 is closer to the guest house area, or the other way around. And 3 and 4 are sort of septic tanks before it gets discharged further. And this biomass building is where their water heating occurs with the wood chips. So we put temperature sensors at a number of places to measure temperature and also measured flow to determine how much hot water the system was using. I won't present all of these results. I think there'll be a bit more detail about that in our next presentation on heat recovery. But I'll just look quickly at the kitchen results because those were the most promising results for us, at least. So the kitchen temperature was kind of as expected. They used hot water quite a bit throughout the day, up to 100 liters at times, but usually in 50 to 60 liters, and predominantly around lunchtime when the site was busiest, and obviously they didn't do dinner or anything, so closed then. And in terms of the actual temperature of the water, it ranged to a maximum of about 45 degrees, which is very good for heat recovery during the busy times. Not so great at the rest of the times, but still probably doing something there. So in terms of the actual feasibility aspects of what we saw, we also noticed that there was a nice vertical drop in the kitchen drain, which could accommodate one of the vertical heat exchangers that Ajit talked about, one of those copper ones, which is just commercially available shower heat exchangers, essentially. As I said, we sort of said the septic tank wasn't feasible because it's quite far from the rest of the castle, and there was a lot of heat loss before the wastewater got there, and with mixing with the other sources of wastewater as well. So we identified the kitchen drain as having the most potential, especially with this vertical drop as well as the temperature that exists there. In terms of hard numbers, I think our analysis sort of said we'd be looking at a range of savings based on yearly savings based on how much, based on the input source. But because they were using biomass, it was quite low. I think electricity was the most ideal in terms of offsetting costs. And the payback period was around 9 to 10 years. Now, I won't go into too much detail about this because the next webinar is focused entirely on this and on recovering heat from commercial kitchens. So if you're particularly interested in this aspect, I'd really suggest you go there. I think they've got a software you can play with as well to figure out whether it'll work for you, and what sort of better scenarios you could have, what sort of flow rates you need to have to make it worth your time to recover heat from your kitchen. So we'll move on to our second feasibility study that we have looked into. So this is a meat processing plant in Tipperary. So for those of you from an industrial point of view, that might be interesting. So this is a Irish meat processing plant. I think they process beef predominantly. They have on-site wastewater treatment. So that's the picture over there. and they use heavy fuel oil for heating water, and I think that sort of played to our advantage in terms of the feasibility there. So this is the sort of monitoring we usually do. This is this little tiny waterproof sensor that we put in at a few different parts of the treatment plant. So we decided to focus our monitoring on the treatment plant itself because there were some issues with access to the meat processing plant. And I think they had a suspicion and they knew that their wastewater temperature was really high coming into the treatment plant. So we monitored at a few locations, the inlet to the plant, the outlet of a treatment process called the dissolved air flotation. So we chose this dissolved air flotation tank because it was quite early on in the treatment process. And it also had a great vertical gradient as well. So the heat recovery through a commercial vertical heat exchanger would be very feasible in that tank. And we also monitored the temperature of the final treated effluent as well. Now, I will show you some of our results first. So the wastewater inlet temperature was quite high at times, so up to 40 degrees through the days that we monitored. So you can see we monitored for about a month, I'd say, in this one. And the outlet of the DAF tank, similarly, besides this sort of blip here where there was some maintenance work, I think, sort of follows a similar trend to the inlet because it's quite early on in the process and has a lot of the temperature still in there. And the outlet temperature, it's after all the treatment processes, it's sort of equalized a little bit to the air temperature, so it's not as high, but still has some potential to recover the heat because it's still probably below above air temperature there. So in terms of feasibility, we saw very good feasibility for the meat processing plant at least. So in the outlet of the DAF tank with direct heat recovery, so with those heat exchangers, sort of those vertical heat exchangers or other similar commercial copper heat exchangers, we would start seeing very low paybacks of 4 to 5 years, despite, and similarly, if we used a hybrid system, which was sort of using both heat exchanger and heat pump together, despite the high installation costs, we still were getting great savings and a very low, even lower payback period over there. This is just because the heat pump is just able to extract so much more of the heat than the heat exchanger that it's just can offset a lot more of the costs essentially. So this sort of scale, it's really, really like ideal to have a heat pump in there. And even in the outlet where the temperature was quite a bit lower, as you guys saw, it was still quite good for the payback period in terms of 4.5 years. So there's less heat, so there's less cost offset overall every year. But the installation costs are a bit lower because you don't have to have both heat exchanger and a heat pump there. We could just use a heat pump directly because the water is cleaner. And I think we've got one more. Come on. Sorry, guys. All right, there we go. So the last site that we started moving up in scales here. So this is the next bigger scale that we've got in terms of feasibility study. This is a municipal treatment plant in County Offaly, also in Ireland. It's pretty standard treatment process. There's some settling tanks, some aeration tanks, some clarifying before it's discharged to the environment. The good thing about treatment plants is that they have to do temperature and flow monitoring themselves before they discharge. So we have some ideas. So we didn't have to do much monitoring here because there was quite a lot of data already available from the treatment process. And based on that, we knew how much effluent. So we focused on the discharge over here for heat recovery. Heat recovery from the inlet is also possible, but there's potentially some issues with how it affects treatment. So we focused on the effluent and the discharge point here because that was no troubles at all in terms of recovering heat from that part of the treatment process. So the average flow was quite high. So we're looking at about 7,500 cubic meters a day. And the temperature also reasonably follows sort of air temperature. So higher in summertime and lower in winter, autumn and spring. But overall, on average, about 16.5 degrees in terms of effluent temperature. So in terms of feasibility, it's difficult to put actual numbers in such a large system because there's such a large heating demand. You can't really ignore the fact that a lot of infrastructure is required to actually use that much heat. So we're talking about 2 to 3 megawatt power heat pump. And the payback just for the heat pump itself could be as low as 2 years if there was a demand for the heat. And one of our colleagues, Jan, previous colleague Jan, has done quite a bit of work in looking at the neighboring districts around the treatment plant and trying to match heating demand with the available heat from the treatment plant, and found that there was opportunities to go ahead, just that there was a requirement of the existing infrastructure for district heating or something else that it could be used for. So it's hard to estimate feasibility, but there's definitely an opportunity if there is some sort of additional infrastructure in place. Now, so the key sort of takeaways from our case studies, at least as far as we found, and we'll discuss these some more in the next slides, is there is a significant opportunity for rainwater heat recovery, especially in larger commercial kitchens, in industries, and even in municipal wastewater treatment plants. The feasibility of the scheme, as Ajit said before, it really depends a lot on the temperature and the volume of the rainwater. But the type of fuel you're putting off could also determine the feasibility of the system with quite a high, could have a quite high impact on that. We'd like to build a bit more confidence in our monitoring results, because I guess they're all sort of theoretical for the moment. So we've gone ahead with some pilot installations, which we'll talk about in the next few slides. And we talked a lot about the commercially available heat exchangers now in terms of those shower type heat exchangers, which are quite efficient, but we'd still like a few more technology options available. So that's another pathway that we're sort of looking at to improve uptake. And that sort of brings us to the last topic of the presentation, which is improving uptake. And so we'll focus on this, on just sort of the three different things we sort of focusing on to talk about to reduce uncertainty in implementing rainwater heat recovery. So the three things we're looking at is monitoring. So we've looked at 3 sites that we've done some monitoring and some analysis on the temperature to identify what sort of opportunities are there. But we've done quite a few more than that, and we'll just have a quick chat about that. And the second is we'll talk about 2 pilot systems that we've put into place and some initial results from one of them. And the last one is sort of the work we're undertaking to have broader technology options and sort of improve how we implement rainwater heat recovery and improve the opportunities for it. So we'll just talk about the monitoring first. So in total, we've monitored 15 sites for both wastewater temperature and flow in some cases, not all of them. As you can see, we've got a large number of food and beverage manufacturing sites that we've monitored, about 53%, a lot of commercial kitchens as well, a few municipal sites, including townships and treatment plants, and some community centers. We're always keen to expand the areas that we monitor. So if you're interested in us doing some monitoring for you, we'll just get in touch with us. We'll have our details at the end. We'll send you some sensors to install those little ones that you saw, and you can get in on the action as well. I saw there's some people from the HSC, so we're particularly interested if you guys are around in doing some monitoring of hospital wastewater after COVID, of course. And yeah, all right, cool. And the second part of improving uptake is I'll just have a quick overview of pilot installations. So we had the budget to install a couple of heat recovery systems to look at issues with their longer term operational. So since we had a sort of good site in Penrhyn Castle and they were interested in us going ahead with this sort of work as well. So we did install a heat recovery system in Penrhyn Castle. So the system sort of does 2 things. It does a sort of indirect heating. So it has an intermediate tank where the rainwater goes through a heat exchanger, which is stored in an intermediate tank before it goes to the wood chip heating system. But it also has a direct heat exchanger where the cold water goes through the heat exchanger and goes straight through to the other heating system. This is just so we had the kind of capability to install both these systems in place. And we just wanted to compare and contrast to see if there was a big difference in operating one way or the other way, if there were any serious benefits. So the main aims of this installation was, of course, to monitor the data and investigate the scope available in Penrhyn Castle for heat recovery and whether there's any change in the heat recovery over time. But what we were hoping more broadly is also to generalize any results for commercial kitchens in general, because we see that as a real sector with lots of opportunity for heat recovery. And this is just some pictures of the system. And as I said, there are 2 heat exchangers. So those long little copper things that you see there are the heat exchangers. One of them goes directly to the wood chip heating system, whilst the other one goes through this buffer tank over here and is circulated through to the wood chip system. And we've got, so just putting it out there that we commissioned this early last year. And we ran it only for 3 months, after which obviously there was the pandemic and the site has not been a busy tourist attraction as it previously was. And so there is the caveat on our results here. And we'll also add in the caveat, another one, because everybody loves caveats, is there are no tourists before February. So this part of our January data set is basically when the kitchen wasn't running at all. So what you can sort of see at least is there is a significant increase in preheated water temperature. So our system works, yay. But we just need a couple, we want to run it before we make any serious analysis of the feasibility of installing this in commercial kitchens. We'd want to run it through the busiest time and figure out whether the system works as well, whether there's any change, run it for a bit longer. So at the moment, all we can say is the system does work and we are preheating the water significantly. But as to whether the longer questions about feasibility and how effective, that will have to wait till we can run it properly again, hopefully this year or next year. This is sort of have similar caveats for the second system where we've struggled as well. So we've developed this little pilot installation, sort of like a portable mobile system to use at the treatment plant of the meat processor that we discussed in Tipperary. So we're looking at recovering heat from their treatment plant through a sort of combined system using both the shower heat recovery systems as well as a heat exchanger attached to these, serving as the heat exchangers. It's sort of like an indirect or hybrid system as we discussed. So that's what the system looks like completely installed. It's got a little pump on top to drag water out from wherever it needs to. It goes through the different heat exchangers. There's lots of data monitoring, looking at temperatures and flow and etc. And there's the heat exchanger in the back that you can't really see. So the main aims for this one was us doing something similar as before, looking at the inputs, how it worked over time. The water in the meat processing plant was, the wastewater quality was not great. So I think someone had a question, I think John O'Shea from Prodema, about the long-term efficiency of fouling, etc. on the heat exchanger. So when we run the system for a bit longer, we'll have some more clear answers about that. And that's one of the main questions we'd like to answer as well. If you use wastewater that's quite heavily polluted, what are the potential impacts on heat recovery over time? Do you do anything to the heat exchanger in terms of copper or something else? We'll also look at maybe. But we'll sort of say that we've had a few issues with operating the system, mainly because it's just got more moving parts than the other one. And we've had to pump it in. We had some water quality issues with the inlet pumps being blocked. We also had to work around the operational treatment plant of the meat processors to make sure we didn't impact on their operations. And we used it at a few different sites. So we don't really have any long-term results. We've run it for about 3 weeks before we had to stop running it. And I'll hopefully get a chance to go down to Tipperary and run it some more in the next few months. So see how that goes. Now, the last part of the presentation is sort of some of the novel methods we're looking at to improve existing technology. This is something that Ajit is working on. So this is a picture of a grease trap. So this is something that's ubiquitous in commercial kitchens. So the kitchen wastewater, which often has a lot of grease, goes through this little settling grease trap to remove the grease. Well, the opposite of settling, I guess it rises. And before it gets discharged to the sewer. So we see the grease trap as a real point of opportunity to recover heat from, because the water is there for some time, is retained. It's often hot. So we are looking at sort of developing a grease trap that also has a built-in heat exchanger and potentially commercializing it. So this is our actual grease trap in our lab. This is the hot water tank that supplies it. And these are all the sensors that measure the temperature. And there is already a heat exchanger in there. And so based on these physical experiments and lots of modeling that Ajit is working on, we'll go a bit further in terms of looking at where to put the heat exchanger, what material it can be, the size, before we sort of start looking at commercializing this sort of technology and moving it forward. We're also thinking of using a sort of similar methodology for something like the dissolved air flotation tank or other wastewater treatment processes, especially in industrial sites. Sort of trying to look at integrating heat exchangers within these sites, or at least giving ideas for where they could be integrated for other people to do if we can't do them ourselves. So we'll sort of getting towards the end of the presentation now. So I'll sort of summarize to say we think there are significant opportunities for rainwater heat recovery And we've sort of identified some opportunities through monitoring and some feasibility studies, but we're always keen to do more. And we're always happy to try to look into any questions that people might have. We've got two pilot installations to identify any changes in our heat recovery and any maintenance issues. Hopefully with more data coming in 2021, watch the space. And our final part of our research is sort of looking at improving uptake and hopefully commercializing some new heat recovery technologies and getting some ideas there. And I'd like to thank you all for listening. And this is my tribute to the Ireland-Wales project for funding us. Gaurav, Marva, Gwiv, and Diolch to everyone. Thank you for listening. Thanks, Roberta, for setting everything up. And thanks, Angus, for introducing us, and Ajit for his part of the presentation. I'll leave the slide up there so that you guys get all our email addresses and stuff. And you can send us an email if you are ever interested. But we'll leave this here for questions. So we'll see if, I don't know what other questions are there, but we'll start off.
Great. Yeah. Thanks very much, Madhu. That was very good. And thanks for your Irish and your Welsh, although I'm not qualified to say whether your Welsh was good or not. So very good. So on the questions, as I mentioned at the start, any questions you have, please feel free to put them into the chat. We had two very good ones to begin with. So the first one was from John O'Shea, and you touched on it. So John was asking how fouling of the heat exchanger is addressed in the current design concept to ensure heat exchanger remains efficient over its lifetime. So I might try and answer that broadly, and you, Madhu and Ajit, you could chip in at any point if there's something I'm not mentioning. But so fouling of heat exchangers in drain water heat recovery, I think, is a general issue that is more or less important depending on the setting. So and heat recovery from wastewater is also more and less straightforward depending on the setting. And so when we went right back at the start and we used the example of a shower, the idea of recovering heat from a shower drain is around for a long time. And in certain countries, for example, in parts of the US or Canada and places like that, that has been quite standard for many years, you know, more than 20 years in places. And so there are commercially available systems there that work very well, and they don't really suffer very much from fouling. And if you think of the nature of the wastewater that goes into the shower, it's not particularly polluted. But then as you move further up the scale into, for example, our meat processing plant, the raw wastewater is highly polluted, and in that case, the answer to John's question there is a bit unknown, and so we are kind of developing heat exchangers there to try and assess that, and hence our little pilot there is a mobile one, which we're able to move around from the inlet of the treatment plant there, where the wastewater is quite hot but very polluted, to the outlet where it is, you know, 20 degrees and clean. So the answer to the question is not fully addressed. So you know, there is more and more commercial focus on trying to exploit this, and there are companies appearing who you know, let's say in the marketplace, who offer solutions to try and do this on different scales. There are a few companies around trying to you know, offer sewer pipes, for example, that have heat recovery within them. There's a few companies offering systems for wastewater treatment, which is where the wastewater is very, very polluted, like Shark Energy in the UK, and others. So I guess it's a developing field, and I think the most complicated one would be to try and recover heat from a wastewater treatment plant, because there's so much heat available there. Talking about megawatts versus, like in the shower situation, it's probably a number of watts. You know, I don't know. Does it reach kilowatts? Probably doesn't. So the scale of the problem is different. And so it's a developing area, and that issue isn't fully addressed, John, I guess. I don't know if Madhu or Ajit have anything to add to that.
I think you've covered it quite thoroughly there. I think we've I think it's something we'll investigate some more. And I think Angus, you're right, but it really depends where where the wastewater is coming from. But
Yeah.
the shower probably not a big issue, whilst the meat processing plant might potentially an issue.
Yes, exactly.
The fouling in the grease trap system, we are going to evaluate with the edible oils and some fat oil and greases. So it is under progress. So for the further results, we'll definitely come and report. And
yeah, so that I guess that relates then on to Martin Hughes had a question about will heat recovery increase the risk of fatbergs? If so, what can be done to mitigate this? As we do need to recycle the heat if possible, right? And so that's a very good question as well. And if I was even to generalize it, it's worth thinking about what is the impact of recovery of heat from wastewater on the wastewater system itself, the sewers and the treatment processes. So both of those things are in our minds at the moment. So if we recover heat from wastewater, it obviously reduces the temperature of it. I think wastewater heat in sewers is not so well understood as the dynamics of that, how the temperature changes from when it leaves your house to how it gets to the treatment works, hasn't been really very well monitored, and that's why we started off doing a lot of monitoring to begin with, as it wasn't something that data that normally collected as there wasn't really a focus on the recovery of that waste heat. So what we're concerned about is that in the treatment plant setting, some processes are temperature sensitive, and if we were to recover heat from certain areas of the wastewater treatment works where there is a lot of heat available, it could have an impact on the efficiency of the treatment process, and obviously we would have to try to avoid that. And there, in certain countries that are more advanced in this than others, Ajit, for example, presented a chart of countries carrying out a lot of renewable heat of different kinds, but in certain countries there are regulations about how much heat can be recovered from wastewater. I think in Germany there may be one, and also in Sweden or Switzerland.
It's Switzerland,
yeah,
Switzerland, right?
Yeah.
So to try and avoid those impacts, and that's a kind of a catch-all scenario to help avoid impacts on treatment and also formation of fatbergs. Then to get to the question directly about fatbergs, I think in short, we're not sure at this point as to how it would impact fatbergs directly. What we are doing about it is through the work with Ajit on grease traps. So if you're familiar with grease traps, there are a requirement for any commercial kitchen to try and avoid grease entering the system. One of the issues with the operation of these is that they are too hot, and as you know, if the wastewater is hot, the grease trap will work less efficiently. So we're trying to work on a system which will extract some of the heat directly from the grease trap, because it's a very convenient location. In one of the diagrams that Ajit presented for a building, there's a requirement for some kind of a holding tank. You've got to capture the wastewater in one place for a while to extract the heat out of it rather than it directly flowing down the drain. And so a grease trap is something that exists already that does that function. And if we take heat out of it, then I guess it makes the grease trap more efficient as well as recovering waste heat. So that might address a little bit the fatbergs, but not every. Go on, sorry.
There's a couple of papers that have looked at this sort of an initial study on the effect of temperature on grease in sewers. I think it's even their study was sort of inconclusive. It didn't say whether a colder temperatures would make it worse or not. It was sort of the same so far, at least.
Yeah, exactly. And so if you were to recover some heat from the sewer outside of your house, for example, it's not that heat would eventually recover, to whatever the ground temperature was. And so it's a complicated combination of the air temperature and the sewer, the ground temperature around it, what else is joining it. So it's not as if you take the heat out, that loss of heat stays in the system all the way to the treatment works. We are thinking about trying to model all of this, but it is a work in progress, so we will try and do something about it in the next couple of years. So there were a couple of other questions there.
What about heat storage? I think from Janet, she said.
Janet, yes.
I am thinking that would be an issue more for domestic cases. So that's just a quick note on the heat storage. That so what we're trying to do at Penrhyn Castle, at least with the insulated intermediate tank, is a sort of form of the heat storage. But I think the viability of the heat storage is only comes into it for larger systems, because especially at the household or maybe sort of like kitchen scale, moving towards larger kitchens, the initial cost is the initial cost of installation plays quite a high impact on the feasibility of the system. So we might adding in heat storage might just push it over to it not being feasible, even if you're getting more heat. So it's I think the heat storage it's definitely an interesting question. But I think it's more valid for larger systems. I don't know if you guys have any.
If there is some larger variation in the volume flow rate and the availability of the temperature of the hot wastewater, so we can have a better option to place an thermal recovery unit there, just like an phase change material or something, to recover the heat for some amount of the time, so that it will recover directly from the heat storage unit. So it will compensate the energy as well as the flow rate. It will compensate. Yeah.
So just following up on that, we didn't focus on it very much in the presentation, but we did in the beginning of our work on drain water heat recovery look a lot at the domestic sector, and so our main finding was that if you were to try and recover heat for the whole building from a 4-person house, that the economic viability of that would be fairly marginal, because there isn't enough flow and temperature there which combine to make the energy to make that viable. So but that's not to say that if you were to scale up into more densely populated building types like apartments or housing developments of some kind, that it would be feasible there. But the issue of energy storage in that case is important, because the time and when you need to use the energy and the time that the hot wastewater is available, they don't match exactly. There is a lag between the two. And so in our pilot in Penrhyn Castle, for example, what we were trying with the little storage tank was to match those two differences in the requirement for energy and the availability of the waste. So as Matthew was saying, it adds more cost, but we hope after a full tourist season to have the answer as to whether it's actually worthwhile there. The domestic setting, it doesn't seem to be.
No, sorry, Angus.
But for the showers as well, so as I was saying, that wastewater heat recovery in showers has existed for a long time, and the savings, if you run the figures there, the savings that you would get from installing one of these in your own house, they are also quite marginal. It's not, you're not saving a huge amount, so the payback period could be quite long. So as a retrofit, it doesn't really work without some kind of an incentive. Now one does exist in the UK, which makes it, there's quite a market for it there, but in Ireland, I know that it hasn't really been a success. As part of a new build, it makes sense to install, but as a retrofit, those are difficult to justify.
And Janet had one more question. I'll just try to address that, and we can go on to the last question from Camillus. I think in terms of the efficient operation of the treatment plant, Janet, the hot water coming into the treatment plant is about 40 to 50 degrees. Now that's not really great temperatures for the microbes. So there is a sort of temperature at which they plateau, and then they don't go any faster from that. And that's sort of similar to sort of room temperature. 24 degrees is probably the peak operation of the microbes. So that it does raise an interesting question as to whether if we remove a lot of the heat, it might potentially have an impact on downstream processes. So there is some complication there. But I think at least with the meat plant, I think there's enough heat there that we can maintain like a lot of the heat for the microbes to still be able to function and for their treatment to be optimal. So basically, I think that's that one. That's it.
Yeah, exactly. Yeah. So I mean, we don't have all the answers to that just yet, but it is something certainly working into, and our experience of monitoring these it is amazing to see the you know, the steam coming off wastewater as it travels into these drains, it looks as a tremendous waste of energy. So I think there's a big opportunity there, particularly in the food processing sector. Almost everywhere we've gone, from various drinks and food producers of different kinds, seem to universally have a lot of hot wastewater at very high temperatures, at least at the inlets of their treatment plants. So
in terms of the leisure center, Camillus, we had that discussion about leisure centers, which Aisha led, and I think Aisha's here, but I don't know if we can.
Aisha is leading that, but yeah.
Yeah, but I think we also have a Slack channel and some more information about leisure center heat recovery in general and discussions about it. So we've got so Camillus, we can send that through to you if you're interested. So you can join the Slack channel, and I think there's a lot of leisure centers along with Aisha and a few other people who have expertise in recovering heat from that. And yeah, so that's sort of it, I guess, basically for us. I don't think we have a lot of information on leisure centers. Otherwise, I think there's a couple of feasibility studies that colleague Jan has done. But besides that, I don't know if you have anything to add there, Angus.
No, I guess, yeah, on our web portal, or if you contact us, do we have our contact details on the next slide, actually?
It should be on this slide, I think. Is it, or is it?
I mean, the general one for, well, yeah, I suppose you could use our emails here. That will
There is also there is we can sort of slowly go down to the next. So this is the references for us. And we'd encourage you to sign up to the webinars, and Angus has discussed them as well, especially the next one, for kitchen wastewater from commercial kitchens, recovering the heat. And I think we've got our links there. So we've got our website and our Twitter account, so we can.
Yes, perfect. That's what I was going to say. So if you go onto our website just there, we have lots of information on it. We have a members area if you want to join, and we can give you access to more data. So, for example, Rowan Maloney was asking about data sources for Irish flow and temperature data by use case. So some of the things that we're talking about are published, and within the list of references that were just up there, or via you don't need to go back to it, Madhu, but or via the website. So, for example, Ajit mentioned a study on we did a study on the entire UK hospitality sector with flow and temperature data in there. We did it for the domestic sector in Ireland. Those are published, and so those will be good sources of that. Okay, so I think we dealt with all the questions. There is I'm just putting a feedback form into the chat there. It'd be very grateful if you could give us your feedback on how today went and how we could improve things. It would be very helpful. But for now, I think that's it. We're just finishing 2 minutes ahead of time. And again, if you are more interested, we'll be going into a lot more detail on the operation or the design and operation of the pilot plant at Penrhyn Castle. This is a commercial kitchen in about 2 weeks' time, and it'll also be quite an interactive session where we have a little tool for you to try and work out how this might work for your own scenario if you happen to have access to a kitchen yourself. So thanks very much, and thanks to my 2 speakers here, did a great job. So we'll see you again next time.
Thanks, everyone.
Thanks,
Bye.
everyone.